This short tutorial will be taking into account some of the basic features of geochemistry in hard rock petrology, as well as some of the notations taken into account. Now, whenever we are trying to obtain some of the data from a type of geochemical analysis like XRF or ICP-MS, depending upon, or on the major element or trace element geochemistry from a rock, we try to identify the separate types of variables. We try to denote them in terms of separate types of variables. Those are present in the rock. The rock which may or may not suffer different types of evolutionary problems like weathering, metamorphism, etc. and etc. Now the thing is that whenever we are trying to obtain this data from different types of analysis, we get different types of plots, like bivariate plot in terms of silica, in terms of different major oxides, as well as we try to get the idea about the elemental fractionation or melting during different types of evolution of the or different types of petrogenetic process that undergoes in a rock, whether it is partial melting, whether it is fractional crystallization. This is a short note, or this is actually chapter 9 from John Winter's book, and this PPT, it will be very much necessary for you to understand the processes which might affect a rock or after its genesis or during its evolution. These separate types of minerals, as we have known, or regarding the idea of distribution coefficient or partition coefficient, which is often told as concentration of the, it is taken as a concentration of whenever a melting is taking place, then the amount of the, or the concentration, or rather the mass of the element that goes into the melt by the mass of the element resting in the solid phase. So this thing is very important, and a partition coefficient, or depending upon the partition coefficient, mass of the element going, that's the melt, and the mass of the element that is a solid phase, where sometimes the ratio is known as d prime, which is actually dependent upon the kd, or depending upon the pt as well as the IR and charge in a situation, as well as activation energy if broken in a melting by Gibbs minimization this process is going to operate and give away the elements away from the rock. The concentration of rather the mass by volume is taken into account by different types of analysis like ICP-MS or maybe sometimes XRF can also give you some trace element analysis also, but ICP-MS is exclusively used for the purpose of rare earth element analysis, or even like elements analysis like IPG or PPG, etc., etc. Now, when the paper of the ray camper, I have told you that these things can help us to identify or to as well as analyze from where the rock had came from by the partial melting, and the partially molten rock, obviously partially molten, whatever the state is, whether it is melt or magma, it is going to crystallize at an instant or a point of time. So that's how these things are going to happen. Now, this type of diagram where the base or the x-axis is denoted or is taken into account in terms of the SiO2 percentage analyzed in a rock, and the y-axis it is taken at the other major elements. These types of plots are known as Harker plot or Harker diagram. I hope that you guys know how to do this type of thing, and then obviously you can also change the axis, you can edit them. Suppose here the data is in terms of SiO2 versus magnesium oxide in a fractionating rock where the composition of the basalt or the composition of the rock is changing from basalt to basaltic andesite to andesite to dacite to rhyodacite composition. Now obviously you have certainly known the igneous classification scheme, and we have done quite a part of a good syllabus from the igneous petrology. And now this x-axis, and if I now try to replace this y-axis in terms of calcium oxide, I have just to replace with this, and then the result will be looking like this. So obviously there is a change in terms of the theta or tan theta of different points with respect to different elements as the concentration is changing. However, the trend, what it is showing is that with increasing amount of silica, the magnesium oxide or the calcium oxide content in the rock is diminishing. Why should this happen in a rock? This will happen because from the basic idea of petrology or basic idea of igneous petrology, we often see in case of a basaltic rock or any mafic rock in field that the earliest crystallizing phases in a mafic rock or an ultramafic rock is olivine or clinopyroxene. Now what are the elements they might bear? Olivine and clinopyroxene do bear some amount of magnesium, some amount of iron, some amount of calcium in them. And then obviously if we try to analyze a rock, suppose here I am trying to draw is this, a magma or blob of the magma is rising upwards, and slowly by crystallization of different elements, suppose the crystallization is shown in red chamber or red things, or small crystals are crystallized, and these are like composed of olivine and clinopyroxene, etc., etc., and these are forming the restite or crystals which are at the base of the chamber, and the rest of the magma is then this amount, and then they are rising upwards in this direction. Then obviously at the base of the chamber, what are the minerals which we might find out are olivine, clinopyroxene, and then the chamber or whatever it is, this is changing its composition, and the crystallized materials are changing its composition from olivine or clinopyroxene to some orthopyroxene maybe, depending upon the carbon dioxide or H2O partial pressure in the rock, because more or less in these cases they are important, as well as some of the plagioclase is crystallizing with some clinopyroxene also. Then the thing which is going upwards at the latest stages, what it is going to crystallize is quartz and some mica with it. So obviously the most important phases or most important elements which are going to get crystallized in these silicate phases are like magnesium, ferrum, calcium, silica. And the thing is that with increasing silica content, that is along the x-axis, the lower the silica content, the higher the magnesium. The lower the silica content, the higher was the magnesium oxide, and higher the silica content, the lower is also the calcium oxide. This is in terms of magnesium. What we are observing is that. And if we try to choose same in terms of, or we try to observe in terms of aluminum oxide, in terms of iron oxide, we can see that there is sorry, PO versus silica. The x-axis value should be iron total. So why is this happening? This is a very bad thing. This thing should not happen like this, because editing. Okay. So I was wrong actually. The silica value is this. Silica value should be x-axis and the y value should be y-axis. Now this is okay. Yes, the iron oxide will also show a decrement in the amount with respect to, or we can also plot multitudes of data in this region by adding, suppose MgO versus silica, and then I am putting the value of x in place and y. Then this, okay, then I can put another data in terms of, you can see clearly that the iron oxide and magnesium oxide, those data can be separated by the color as well as index. And if I add some of the calcium oxide in this series, CaO versus SiO2, and then X value will be, Y value will be. So that's how these types of diagrams can be built. This is a simple Harker plot, that is in terms of a bivariate plot, and that's how we can say that olivine, orthopyroxene, clinopyroxene was crystallizing when the crystallized rock had more proportion of olivine and pyroxene in them, and because the olivine is a much more silica under saturated mineral as well as clinopyroxene is less richer in silica with respect to feldspar. The silica content in the earliest crystallized basaltic fraction is low. On the contrary, the concentration of the elements like iron oxide, calcium, magnesium oxide are high. With the crystallization, which is going to advance with time, and depending upon if we see that the crystallization is happening towards this direction, and we try to analyze this chamber and this chamber and this chamber, slowly we will see an increment of the silica content. And no doubt there will be other processes in a magma chamber non-ideal to this characteristic, and there will be processes like assimilation taking place, and there will be zone refining as well as melting, as well as maybe peritectite enrichment. There will be several mass balance processes, but these are more detailed things which we can know but later on. Okay, now that's how this thing is going to get operated in an igneous rock, and this series may be known as a classical Bowen's reaction series of igneous fractionation or igneous crystallization. Now, this is a very important thing. Slowly this thing is going to be pretty much, I mean, small change in composition, and the Harker plot will certainly tell us how the fractionation did take place. Another interesting thing I would like to tell, that if I try to select some of the aluminum oxide data, series X value SiO2 and series Y value will be then there is an increment of aluminum oxide in the rock by the or during the analytical process. Now, why is that? This has a very technical answer, is that during the crystallization process in the lowest chambers or lowermost chambers, there were no plagioclase feldspar crystallized. Rather, the crystallized phases were clinopyroxene, orthopyroxene, olivine, etc. None of those phases bore any type of aluminum oxide in them. And the bulk rock data is actually analyzed in terms of a 100 weight % basis, where the different types of oxides like silica, aluminum oxide, iron oxide, etc. Silica, aluminum oxide, iron oxide, etc. are taken into account. The thing is that whenever we are trying to get it in terms of 100 weight %, so obviously because there were no phases of bearing aluminum oxide at the base of the rock, as well as the aluminum oxide was getting much more enriched inside the rock, so obviously the aluminum oxide concentration after the basaltic crystallization will be much more increased in concentration. Aluminum oxide, which will crystallize some of the plagioclase feldspar, and because of the plagioclase crystallization plus minus AFS crystallization, the magma, the crystallized rock will bear aluminum oxide in it or them. Now this is how the thing is going to work. Now that's why there is a notch in the aluminum oxide crystallization, because of the sequence in a classic example like we are observing this right now. Now this will be the end of part 1 of this video.